Welcome to AI Paper Slop, the YouTube series where we summarize AI and tech papers for you. Today we are looking at test time scaling in reasoning LLMs, inference regimes, evaluation, and reproducibility. It's by researchers at Case Western Reserve University. And I just want to give you the zero-fluff summary right out of the gate. Test time scaling is not a single monolithic thing.
Right, it's definitely not.
It is a diverse set of inference algorithms that operate over an autoregressive prefix tree. The paper basically proves that to evaluate reasoning models today, we have to evaluate the entire inference system. The prompts, decoders, search controllers, reducers, stopping rules. Not just the model weights.
Yeah, evaluating just the model weights is, well, it's pretty much a dead end now.
Exactly. And to back this all up, they released a massive dataset. Nearly 2 million reasoning traces across math, science, and reasoning tasks. So our mission today for you, the AI researchers and ML engineers listening, is to unpack the exact taxonomy of these inference regimes. We're going to get into the hidden math of decoding gates and why naive best-of-n scaling can, ironically, destroy your model's accuracy.
Which is such a wild finding. I mean, we really needed this formalization because, let's be honest, the whole concept of test time scaling has just become this sloppy buzzword in the ML community lately.
Oh, 100%. It's just thrown around everywhere.
Right. Researchers are currently treating wildly different algorithmic approaches. Like, on one hand, you have sampling multiple completed candidates, and on the other, you're searching over unfinished partial states. And people act like they're completely interchangeable. They just lump it all under this single scalar metric called a compute budget.
And that completely obscures the actual procedure being evaluated. I mean, if you are an ML engineer reading a paper and it just says, we scaled test time compute, you literally have no idea what they actually built.
None at all. It makes cross-paper comparisons nearly impossible.
It's like, okay, evaluating a test time scaling model just by looking at its checkpoint weights is like evaluating a race car by only looking at the engine block. You are completely ignoring the steering system, the driver strategy in the corners, the tires, the prompt, the decoder, the search controller, the reducer. Those are your steering and tires.
That's a great analogy. The engine block is just the base autoregressive model, but the inference algorithm is what actually drives the car around the track. Because the open weight ecosystem has evolved so rapidly, right?
Yeah, totally.
Like, we've moved from simple chain of thought elicitation to models with explicit reasoning controls like Qwen3 and verified distillation like DeepSeek R1 Distill.
So since we obviously can't treat test time scaling as this one big bucket of compute, how do the authors structurally categorize it? Because they have this specific taxonomy, right?
Yeah, they formally categorize test time scaling as budgeted inference over the implicit prefix tree. So for the listener, just visualize a prefix tree as this massively branching pathway of words. Every token generates new branches.
Right.
And your budget dictates how many of those branches you can explore. So they break it down into 3 distinct structural regimes.
Okay, let's unpack those. Regime number 1 is single trajectory sequential scaling. What exactly is that?
So this is allocating compute to one evolving response. There's no branching frontier at all. You're just forcing the model to deliberate longer on a single path.
Oh, like the budget forcing we see in the S1 models.
Exactly like that. You artificially suppress the end of thinking signal and force the model to keep generating text. The advantage is low orchestration overhead.
Right, you just kind of let it run.
Yeah, but the fatal flaw is that if the model makes an early logical mistake, it has to explicitly self-revise and recover on that exact same branch.
Which brings us to regime number 2, leaf-level scaling. So instead of one long path, you generate a bank of completed root-to-leaf trajectories, like entirely finished answers.
Right.
And then you use a terminal reducer to pick the winner. Things like self-consistency or standard best of n fall in here, right?
Spot on. The candidates don't interact at all until they're completely finished. But then we have the third regime, which is prefix-level scaling.
Right.
This is where you allocate compute based on scores for unfinished partial states, you actively expand promising continuations, and severely prune the bad ones before they ever finish generating.
So architectures like tree of thoughts or Monte Carlo tree search or using process reward models mid-generation.
Exactly.
Okay, wait, let me push back on this a bit. Looking at those 3 regimes, I have to ask about the underlying math here. Aren't leaf level and prefix level ultimately just 2 different engineering methods for generating a bunch of answers? Why do the authors enforce such a strict mathematical separation?
It's because of how prefix-level search actively alters the reachable outcomes. In leaf-level scaling, you are just independently sampling from the model's base proposal distribution. Whatever the model naturally wants to output, you just sample it a bunch of times.
Right, that makes sense.
But in prefix-level search, you are actively pruning the tree early. If your heuristic, let's say a flawed process reward model, decides to prune a branch at step 5, and that branch happened to be the only ancestor of the correct final answer,
Then it's just gone.
it's permanently gone. No amount of downstream compute can ever recover it. Therefore, prefix search fundamentally alters the proposal distribution of the final answers. It literally changes the statistical support of what can even be generated.
That concept of the proposal distribution is so crucial. It completely reframes how we look at basic code configurations. The authors actually argue that the standard decoding setup itself is the proposal distribution, and we are heavily underreporting it.
We really are. They introduce this energy gate view of a one-token sampling protocol. They break down a stochastic decoder into 2 distinct components: constructing a measure, which determines relative weights, and constructing a support, which is the actual subset of the vocabulary that remains eligible for generation.
And we construct that support using different types of gates, right?
Yeah, you have level gates, which act on thresholds, like only keep tokens with a probability above 1%.
Right.
Then you have head budget gates. This is where your classic top K or cumulative mass top pay rules live. And finally, objective gates, which solve a specific set objective.
Let's slow down and look at the mathematical reality of sequencing these gates.
Right.
Because the authors point out something that honestly completely breaks how a lot of us think about reproducibility.
Oh, this raises an incredibly important question.
Yeah, they prove mathematically that a sequential protocol of applying top P followed by top K is absolutely not the same as applying top K followed by top P.
Not at all. To understand why, you have to look at how the probability space collapses. Let's say you have a vocabulary of 100,000 tokens.
Okay, 100,000.
If you apply a top P gate of 0.9 first, you're slicing off the massive long tail of highly unlikely tokens to capture 90% of the probability mass. So you might narrow the pool down from 100,000 to just 1,000 tokens.
Right, and crucially, the system then renormalizes the probabilities of those remaining 1,000 tokens so they sum to 100%.
Exactly. Then you apply a top K gate of 50. You take the top 50 tokens from that renormalized pool of 1,000.
But if you flip the order in your code, the mechanics change entirely.
Completely change.
If you apply top K of 50 first, you immediately enforce a hard numerical cutoff. You grab the top 50 tokens out of the 100,000 regardless of their actual probability mass. Then you renormalize.
Right.
Then, when you apply top P of 0.9 to those 50 tokens, the probability mass might be so heavily concentrated in the top 2 or 3 tokens that the top P gate slices your pool down from 50 to just like 3 tokens.
And that means your surviving vocabulary, the actual tokens the model is allowed to sample from, is wildly different based purely on the order of the functions in your Python script.
That is wild.
Yeah, when you sequence these gates, cumulative masses and probabilities are recomputed and renormalized after each and every step. So if an ML engineer doesn't report their exact gate ordering, their numerical float format, and truncation rules, their test time scaling results are completely unreplicable.
You aren't just missing minor implementation details, you are missing the literal mathematical definition of the proposal distribution they evaluated.
Exactly. And once you define that distribution perfectly and generate all these samples, you hit the next massive hurdle. How do we pick the winner, and how do we save compute doing it?
Right, because generating 1,000 answers isn't cheap. The authors make a very strict separation here between the evidence map and the fixed bank decision rule.
Yeah. The evidence map is about what signals we extract, like verifier scores or internal token confidence. The fixed bank decision rule is how we actually use that evidence to pick the winner. Do we use majority vote? Do we take the maximum score?
So they are 2 completely separate architectural choices.
Totally separate. And when we talk about scaling compute, the authors emphasize that cost can only be legitimately reduced by causal stopping.
Right, you can't just generate 1,000 answers, filter them offline on your laptop, and claim your algorithm is computationally efficient.
Exactly. They distinguish between across rollout stopping and within rollout stopping.
Let's explain how those mechanics save tokens differently. So across rollout stopping looks at the history of completed rollouts to decide if you can save future rollouts entirely. Like, if my budget is 80 answers, but the first 5 answers I generate are all mathematically identical, my across rollout rule might trigger and say, hey, we have a consensus, do not generate the remaining 75 answers. You save compute on the macro level.
But within rollout stopping is much more aggressive. It operates at the micro level. It reads a current token prefix mid-generation.
Oh, so like while it's typing out the answer.
Yes. If you are on token 15 of an answer and the sliding window token confidence suddenly plummets because the model outputted a logical contradiction, a within rollout rule kills that specific trace mid-sentence. You truncate the bad trace and move on.
So what does this all mean for the people building these systems? It means naming a scorer, like saying we use best of n, is totally insufficient. You have to specify your tiebreakers, your fallback rules, whether your scores are raw sums, log odds, or softmax weights.
Because order-only rules behave incredibly differently than sum-based rules.
And with all these variables, it naturally forces us to ask, are standard evaluation metrics even capable of measuring this?
The authors argue convincingly that standard benchmarks are actually failing us here. They're breaking under the weight of this complexity. To evaluate these systems properly, we need to separate end-to-end system performance from the discovery stability profile.
Okay, end-to-end system performance is your capability claim, right? The performance of your fully deployed inference system acting exactly as it would in production. Prompt, model, search controller, stopping rule, everything.
Right. But the discovery stability profile is a diagnostic tool for the candidate bank itself. It measures the latent single-attempt success probability. Essentially, as you increase your budget, how quickly does the generator discover the correct answer, and how stable is that discovery?
To investigate this, they ran a massive empirical study. We are talking over 2 million reasoning traces spanning highly complex data sets like MMOU Pro, Big Bench Hard, AME. And the data point that absolutely blew my mind was from Quen 330B, A3B thinking on the math data sets.
Oh, this is the best part of the paper.
Yeah, the model's base accuracy, just asking it for a single response, was 75.56%. When they increased the sample budget to 80, the candidate availability shot up to an incredible 91.67%.
Meaning there was a 91% chance that at least one of those 80 generated responses contained the mathematically perfect answer.
But here is the trap. The correct answer is in the bank. Discovery is actively happening. But when they applied a standard selection heuristic using the mean token log probability to select the final answer, the submitted accuracy actually dropped. It fell from the baseline of 75 down to 65.83%.
What's fascinating here is this phenomenon of reward hacking or over-optimization.
Right. You gave the system 80 times the compute, the generator produced the right answer. But the selection rule was so flawed, your final accuracy plummeted by 10 points. Why does mean token log prob fail so catastrophically as the bank gets larger?
Well, think about the nature of complex reasoning. A correct reasoning trace might be long and meandering. It might take 40 steps to arrive at the right answer, and mathematically, every additional step accumulates a slight probability penalty.
Because you're multiplying probabilities less than 1.
Exactly. So a correct long answer might have a lower overall mean log probability. Conversely, a confident hallucination might be very short. The model confidently outputs entirely wrong logic in just 5 steps. The log prob is high because it's short, and the model was confident in its mistake.
So when you generate just one answer, you get the model's natural default. But when you generate 80 answers, you vastly increase the statistical likelihood of generating a highly confident hallucination.
Right. As the bank grows to 80, you expose your reducer to more and more of these proxy score errors. The reducer just blindly looks at the mean score, gets tricked by the short hallucination, and picks it over the correct, longer reasoning trace.
The generator is working brilliantly, but our reduction heuristics are failing to pick the right answers out of the lineup.
Which is why, if a paper just reports best of n accuracy without detailing the exact evidence map and decision rule, they might be completely masking the fact that their underlying generator is brilliant, but their selector is broken.
Which points directly to the reproducibility crisis this paper is trying to solve. If standard metrics hide these massive mechanical failures, how can we trust any scaling curves published today? The authors outline a sharp distinction between exact replay and distributional reproducibility.
Yeah, exact replay is basically a strict software audit. Deterministic kernels, fixed batch schedules, serialized banks. It's about ensuring you can get the exact same bits out of the machine.
But distributional reproducibility is what makes scientific comparisons meaningful across different hardware, right? Getting statistically compatible estimates using protocol-consistent uncertainty estimates.
Right. You can't just change the random seed once, run it again, and call it a confidence interval. You need non-parametric bootstrapping over the prompts, and you have to propagate that variance through your specific aggregation rules.
And to help the community actually build these statistically robust systems, they dropped an absolute goldmine: the full data set of nearly 2 million reasoning traces, heavily featuring 2025 and 2026 competition math.
And it isn't just a text dump of the final answers. The signal-rich blocks include the alternative tokens that were considered at each step, the chosen token log probabilities, and both reference-assisted and reference-free verifier scores.
For the ML engineers listening, the utility of this is staggering. You don't have to spend thousands of dollars on GPU compute to regenerate 80 responses per prompt for 20 different models just to see if your new voting math works. You can just plug your new selector into their dataset completely offline.
It accelerates the science immensely. It forces the community to be intellectually honest about where their performance gains are actually coming from. Are you improving the core intelligence or just engineering a better filter?
Bringing this all back around, we started by realizing you can't evaluate a race car just by staring at the engine block. But the mechanical realities exposed in this paper push that boundary even further.
But they really do.
If the exact execution of an inference protocol down to the float precision, the specific mathematical order of the truncation gates, and the token-level causal stopping rules is what actually determines the final reasoning outcome.
Yeah.
At what point does the intelligence of an LLM cease to live in its static weights?
That's the real question. If the search algorithm and the selection heuristics are what actively bridge the gap between 65% and 91% accuracy, then the static weights are no longer the complete intelligent system, they're just the raw substrate.
Are we transitioning away from training intrinsically intelligent models and instead moving toward engineering intelligent systems where the LLM checkpoint is really just a dumb generator of raw cognitive material? It is definitely something for you to mull over the next time you write a generation config. You've been listening to AI Paper Slop. Grab the dataset from Case Western Reserve University, double-check the order of your decoding gates, and we will see you next time.